Okay, so what we've been covering so far is something called diffusion, which again is where you have a single point of some concentration, for example, that diffuses and smooths out over time, and convection, where this is also happening inside a moving fluid flow. Let's call that U. Okay, so we're starting off with a concentration of something. Yes, it's smoothing out, but it's also moving along as we go. Now, it's time to start ramping up the sophistication and a little bit of the complexity of the sorts of problems that we're going to be encountering. So we're going to put on our chemical engineering hats and we're going to consider a reaction where we want to take a species A, which transforms in water into B and then into C, but we're actually interested in B. We want to get the B out of there. Now, most of chemistry you would consider and you would kind of conceptualize in terms of a batch. And the idea there is that you have a single beaker of something. You add in some of your A, it transforms to B and transforms to C, and you might consider timing it or something like that. Many industrial processes nowadays prefer a continuous flow idea. And the idea there is that on top of having this reaction, what you would do is you would put it into some kind of pipe or reactor vessel. You would flow it, and as it goes, it's going to do that reaction. And then you extract your stream on the other side, and ideally you would be rich in B. So this is what we're working up to. Now, let's revisit what, kind of basic chemistry again, right? So the idea here is that you have some species A, which is going to be transforming into B. Let's only worry about the first step here. Okay. Um, there are a few things that we should talk about for this. First of all, this is going to happen with a rate which is proportional to the concentration of A. So first of all, it's irreversible because it only goes one way. That's my beautiful arrow over here. Let me just color it in and try and cover up my mistake here. Okay. But it's also first order kinetics, which means that the rate is proportional to the amount of stuff that you have, which is very intuitive. It's very easy to do. Okay. So R, when we get rid of this proportionality, we make a proportionality constant. And because we're moving this into our framework for computational multiphysics, we're going to call this concentration. Now, this proportionality constant, K, is a rate constant. And a very, very common form of expressing our rate constants is going to be through something called the Arrhenius equation. It's a little bit of a misnomer to call it the rate constant. In this case, let's just call it the rate because it's not a constant, as we'll see. Okay. So a lot of these kinetic properties go like this. You have a pre-exponential, you have an exponential, negative an energy barrier over RT. And the idea with this is that you start off with some species or configuration A, and as you move to B, there's some kind of energy barrier in between. This energy barrier is E, yes, this E, and then what happens is that this needs to vibrate or fluctuate in such a way that it can spontaneously get over that energy barrier and arrive at B, and that's why you have RT there. That's why you have that energetic effect. Now, the important thing is to note that you have the temperature appearing there. And again, computational multiphysics, of course, that's going to be important. Now, as this reaction is proceeding, these reactions, we're told, are endothermic. So the reaction is happening, and as it's happening, it's pulling in heat from its surroundings, which means that while it's proceeding, we're going to have a heat sink, which goes like negative H R, where this is this R here. Shouldn't have circled that because that's confusing with the other ones. There we go. Okay. And H is this term means that it's endothermic. So the reaction is happening, it's pulling in heat, but this actually works out well for our system because it's going to slow down the rate of the reaction itself. It's self-limiting, it's negative feedback. This is actually a really good thing because it means that it's more stable, both numerically and in reality. as opposed to the opposite, which is exothermic, which can tend to get into a runaway type situation. Okay. Now, let's put this back into, so this is our point reactions. Point is also a bit of a misnomer. We shouldn't think about this as points. We should think about this as infinitesimal volumes here. This is happening, all this chemistry, as well as its eventual movement to C, is happening here, 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 and it's producing A, B, and C. But we also have diffusion. So as all these three species are being produced, they're also diffusing, and they're even moving with the fluid flow. So you can see now we have a reaction, diffusion, convection type problem. Already it's complicated. But now we even have the temperature effect. Temperature is there, and we have this heat sink. So as this material is moving through this reactor vessel, we would expect our temperature profile to be decreasing with time, with space. Let me draw that a bit bigger. We would expect something like that. And the idea is because as the reaction is proceeding, it's sucking down the heat. We're engineers, we're chemical engineers for today at least. So what we need to do is we want to replenish this heat so as to control the process. So we're going to add on a heating jacket on both sides of this tube. And that heating jacket is going to add the heat back into the material as it's being consumed by the reaction according to the kinetics, which also depends on temperature. So you can see that it's this big, sophisticated, kind of complicated system. But we can control it. We can control it by the temperature of this heating jacket. And the question then is, what is the optimal temperature of our heating jacket at the inlet, not even at the outlet, at the inlet, in order to maximize the amount of B coming through? So it seems complicated because it is, frankly, but our optimizers are up for the challenge, and this actually makes a very nice tutorial to kind of explore those concepts.